So I posted this tweet yesterday. It says, you have a patient on 15 liters per minute nasal cannula plus 15 liters per minute non-rebreather. What is the speed of the flow you are delivering to them? First option was 15 liters per minute. Second option was 30. And then the third option was it's about the reservoir. And you can see most people picked it's about the reservoir. That was actually a distractor item because this is a question about the speed of the flow that you are delivering to them. So basically what the question is asking is, do you get an additive speed? So if I have two devices at 15 liters per minute, does it actually equal 30 liters per minute of total flow? So you might ask, why does this even matter? Well, a lot of people are doing this for denitrogenation. They're using it for pre-oxygenation for those patients that we're going to end up placing an advanced airway into. And we want to know if adding an extra device is actually giving us any added benefit. You see, we try to give patients as much high flow during these situations as we possibly can. Well, why is that? So when a patient has an inspiratory flow need, we want to try to get as close as we can to matching or exceeding that inspiratory flow need. What does that mean? So if they're breathing in at 30 liters per minute, which actually isn't that fast, and we're only giving them 15 liters per minute of flow, that means that they're going to be entraining room air because our device is not meeting or exceeding their inspiratory flow needs. That is the definition of a high flow device. It meets or it exceeds their inspiratory flow demand. So anything that doesn't meet it is by definition a low flow device. They are drawing in room air. That's not what we want. So how might you look at this problem to try to figure it out? Well, some people would say, and this is actually was my initial thought in questioning this, was, okay, you have two cars traveling down the road. And you got a cop on the other side here, and he says, all right, I got two cars coming at 15 liters per minute. And so he clocks them. Okay, both going the same speed. You would not say that those cars are additive because they're both traveling at 15 liters per minute. Okay, so we're going to come back to that illustration because it's not, solving that problem is not as simple as you might think it is when you look at delivering volume to patients. But you can see how that train of thought might initially tell you that no, two devices going at 15 liters per minute, it doesn't equal, it's not additive. Just like the car is not additive, but is it? So let's consider a different illustration here. We're going to put these into gallons. So we're going to change the air into liquid for a minute here, and we're going to figure out this problem. So imagine you've got, a fourth grade math problem that you're trying to figure out here. And it says your goal is to fill a 300-gallon fish tank in 10 minutes. All right, so you're thinking, all right, I'm going to write 10 ones right here, and then I'm going to divide up that 300 by 10. Okay, so that means that I have to get 30 gallons in every single minute. So let's say that you have some devices they let you choose from, and you're going to do a real experiment here. So I've drawn this fish tank, and behind the mystery door is how I am actually delivering 30 gallons per minute. So we're going to say that 30 gallons per minute is hitting the bottom of the tank. Now let me ask you this question. In just showing you this illustration here, this example, would you be able to tell how I'm delivering that amount of flow to the bottom of the tank without seeing what's behind that door? No, you wouldn't. See, behind that door, I could have 10 hoses that are both running at 3 gallons per minute. I could have 30 hoses running at 1 gallon per minute. I could have two hoses running at 15 gallons a minute. You have no idea what's behind that door. So let's take a look. So we're going to get rid of our mystery door here, and I've got 3, but there would have been no way for you to know that, right? So I have one running at 5, plus one running at 15, plus one running at 10, and then when you look at that and you add it all up, I have 30 gallons that are hitting the bottom of the tank. So you can see that even though none of their speeds are 30 gallons per minute, it's not about the speed of that hose delivering how many gallons per minute it can deliver, just as long as it all adds up to the amount of volume hitting the bottom of that tank. So that's just like our patient. What's going on there is that we have two devices that might not be running at 30 liters per minute, but What they are delivering is what's hitting the bottom of the tank. And so if you were to look at how many liters they both deliver, they're delivering 30 liters into a given space at the end of the minute. And so their speeds actually are additive when you're looking at volume being delivered. Well, what about how fast the patient is breathing in? Well, that wasn't really what the question was about. I could put a drain in the bottom of this tank right here, and that's really not part of the equation. It matters to us how fast the patient is breathing in, but it actually doesn't affect this portion of the equation about how fast we are actually delivering the volume. But it is true that when we give these patients, high flow devices, so we run a lot of volume through their nose, and then we ensure that when they breathe in, they're at least getting some volume through the mouth as well with a non-rebreather, that we are decreasing the amount of dead space. So we are building up a little bit of reserve, and that does make up for some of their dead space, and that does factor into the equation if we were looking at actual volume being delivered to the lungs, but we're just talking about speed here. So let's go back to that illustration. You got 2 cars coming at 15 miles per hour. Well, this is the wrong way to look at this sort of equation, because what you really have is a bunch of units. So if you can imagine that each one of those cars is a liter, you don't just have 1 liter coming through, you have a whole stack of them, right? And then you can imagine that this isn't just a road. Imagine that they're driving off of a cliff onto a pile. So think about this for a second. It's not about how many miles per hour that they are measuring. You wouldn't measure that when you're trying to figure out how many liters are being delivered to the patient. What you would do is look at the amount of cars in the pile. So the liters delivered to the patient is equal to the amount of cars in the pile. And so when you look at this patient, nasal cannula, 15 liters per minute, plus a non-rebreather at 15 liters per minute, it does equal 30 liters per minute because those speeds are additive. When you look at the actual amount of liters that are being delivered at the end of the minute, you do have an additive speed. I hope you guys enjoyed this. If you participated in the poll online, thank you very much for giving your opinion. Digging into this a little bit definitely helped me understand the liters per minute delivered a little bit better. I'll see you guys next time.